So here we had a left bound, here we had a right bound. Now we're going to write a compound inequality statement if there is a left and a right bound. Let's look at this graph. So for this graph that zigzags forever and ever, following this pattern, zigzags forever and ever. By the way, if we wanted it to continue forever, not in the zigzag pattern, we would extend the arrow further. So the fact that the zigzag looks like this indicates back and forth, back and forth, back and forth. What that means is there are many points on the graph where x is negative 1, 2, 3, 4. Many points on the graph where x is negative 3. Many points on the graph where x is negative 2. And every x coordinate in between has points on the graph. So x equals negative 2, x equals negative 2, x equals negative 2, x equals negative 2. I mean negative 4, negative 4, negative 4. Here x equals negative 2, negative 2, negative 2. Our compound inequality then says x can be any value in between negative 4 and negative 2, including those two values. It's a good thing we are such pros at compound inequality statements. Negative 4 is less than or equal to x is less than or equal to negative 2. Here is a similar inequality statement, even though this graph looks really different. So look, we have a left and a right bound for this graph when we're thinking of x and y. The fact that there are arrows, that's not impacting the domain. It's going down forever and up forever, but it's not going forever to the left or the right. Again, we're taking a two-dimensional graph and we're only looking at one dimension, the left and right x dimension. Okay, so this one, no arrows, but a similar domain. There are 2 points on the graph for x equals 0, 2 points on the graph for x equals negative 1, this one and this one, 2 points on the graph for x equals negative 2, 1 point on the graph for x equals negative 3, and same thing for positive 1, positive 2, positive 3. When I'm putting these points on the x-axis, these aren't points on the graph. What I'm doing is I'm translating the fact that there is this point on the graph with an x-coordinate of 1. There is this point on the graph with an x-coordinate of 2. It's really hard for my old eyes to see this. X equals 3. So again, a compound inequality will represent the fact that x can be negative 3, x can be 3, and it's possible for x to be any value in between. X has to be greater than or equal to negative 3. It has to be less than or equal to 3. Think of this as it's between negative 3 and 3. Last two examples where there are no bounds. Here x goes forever and ever and ever and ever and ever to the left. It also goes forever down, but that's not relevant right now. It goes forever and ever and ever and ever and ever and ever up and to the right. All we care about is to the right part. That means that every single possible value of x has a point on this graph. The way we represent this is we say the domain is all real numbers. I like to write fancy R. It is not an IR. It's a bold R. I call it a fancy R. But you need to know that that fancy R represents all real numbers. This graph, even though it looks really different, I'm going to erase these because this looks horrible. This graph has the exact same domain. So yeah, it looks totally different, but we're not thinking about the shape of the graph. We're thinking about what possible x values are there for this graph. X can be 0. X can be negative 1, x can be 1, x can be 2. This point has an x-coordinate of 2. It can be negative 2. And this graph goes forever and ever. Let's just do it. Ever and ever and ever. Oh, this looks so bad. Ever and ever and ever up with an arrow. This graph goes forever to negative infinity, forever to positive infinity, just thinking about left and right. And so the domain of this is also all real numbers. When I'm typing that, I do sometimes type IR, but there's no I involved. This represents all real numbers, and I'm only typing it that way to emphasize the boldness of my symbol. To recap, we are mapping a two-dimensional graph and squishing it onto the x-axis to see what values of x are possible for that relation. we will be using our understanding of inequality symbols to do so. And the only time we won't have an equal to sign is if we have that open circle.